Hello everyone, this is the first tutorial, linear static analysis of a cantilever beam. In this tutorial, you will become familiar with the process of creating a model interactively by using ABAQUS. So first of all, you will create the cantilever beam model and then you'll perform the linear static analysis. So first of all, in the start session dialog box under the create model database, we choose with standard explicit model option. So this area is known as the model tree, and here we have to create a new model. So we double click on the models tab and write the name beam. So right now, before moving any further, we'll save the file. Just remember, whenever you save the ABAQUS file, the extension is .cae, and we press OK. Now we'll create a part, and for creating a part, we'll press on this plus button of beam, and under the parts tab, we'll double click on it. And here a dialog box appears, create part dialog box. The name is kept as beam again. Other than that, all the default settings are accepted. Just the approximate size is changed to 600. Press on continue. And now we have the main window where we can draw the sketch. So what we are going to do is we'll select the rectangle drawing tool, and in this viewport we'll arbitrarily sketch a rectangle. Now using the dimensioning tool, we'll put the dimensions. So this is the dimensioning tool. The horizontal dimension is kept as 200. The vertical dimension is kept as 20. So this is our final sketch, and now we have to extrude this sketch. Press done over here, and the extrusion depth is put as 25. So this is the isometric view of our part. Now the next step is creating a material definition. So to create a material definition, we will create a single linear elastic material with a Young's modulus of 209 into 10 power 3 megapascals and a Poisson's ratio of 4.3. So to do that, we double click on the materials tab, write the name of the material as steel, and under the mechanical tab, we go to elasticity and then elastic. Here we put the Young's modulus and our Poisson's ratio. Press OK, and the material has been created. Now we have to define and assign the section properties. So we will create a homogeneous solid section and assign it to the beam. And the section that we will refer to the material is steel that we just created. So to do that, in the sections tab, we double click on it and write the name as beam section. Other than that, the category and type is kept as default. Press on continue. The material is steel like we want and press on OK. So now the section has been created and we have to assign the section definition to the cantilever beam. So in order to do that, we go to the Paths tab, expand it, and expand the Beam tab as well. Over here, there is this option, Section Assignment. We double click on this. And now we have to select the regions to be assigned a section. We want to assign the section to the entire beam. So we are going to see the, select the entire beam. You can see the beam being highlighted. We click on that. It has been selected and we then click on Done. So this dialog box edit section assignment. The section is beam section as we named it before. We press on OK. You see the color has changed, which means that the section has been assigned to the cantilever beam. In the next step, we have to assemble the model. So we go back to the model tree. Here the tab assembly. We double click on that. So we click on the plus button to expand and we double click on the instances. So over here, we create an instance and everything is kept as default and we press on OK. So after the instance has been created, we have to configure the analysis. So to do that, we first create a general static analysis step. And to do so, we double click on the steps tab and a create step dialog box appears. We can name the step as beam load. The procedure type is kept as general and static general over here. Don't change anything. Press on continue. So this edit step dialog box appears. Here the description can be added as load the top of the beam since we are going to do that. In the incrementation tab, we change the increment size from 1 to 0.1. The others tab, we don't change anything. Everything is kept as default and press on OK. So the step has been created, beam load. Now we have to apply the boundary condition. So this tab BCs represent the boundary condition. We double click on this. So over here, the step is chosen as initial. And this is our first boundary condition. And we can name this as fixed. So make sure that we change the type for the selected step as displacement / rotation. Press on continue. And now we have to select the region where we want to apply our boundary condition. So the region where we apply the boundary condition will be fixed. So ideally we'd want to apply it to this region. And we can do this by rotating such that we are easily able to select it. So this region, we'll select this region and press done. So here a dialog box appears and we'll toggle on the U1, U2 and U3 only, since we only need the translational degrees of freedom to constrain. Press on OK and the boundary condition has been applied. So now we have to apply the load on the top of the cantilever beam. We go to the loads tab, double click on it. And over here, the step is kept as beam load and we can name the load as pressure. Similarly, for the type of the selected step, we choose pressure. The category is kept as manual, mechanical, and press on continue. So now in the viewport, we have to select the surface where we want the pressure to be applied. So basically it should be the top of the beam. We select this top face. You see it's highlighted. Now we press on done in the prompt area, and the magnitude is kept as 0.5. Other than that, the amplitude is RAM, and we press on OK. So the pressure has been applied on the top face of the cantilever beam. So the next step is that we have to do the meshing. The next thing is to go on to the mesh module. We press on, double click on mesh. You see the color has changed, and which means that we have entered into the mesh module. So in the main menu bar, we go to the mesh tab, control, and we choose the element shape as hex. If it has not been, if some other element shape has been chosen as default, we change it to hex. Press OK. So now we go back to the main menu bar and choose element type. And now it asks us in which regions do we want to apply the mesh. Select all and press on done. So this element type dialog box appears. We keep everything as it is. We don't make any changes. Press on OK. So after choosing the so after assigning the ABAQUS element type, we have to mesh the model. So we seed the part. We go over here. This button represents seed part. Press on this, and the approximate size is kept as 10. Press on OK, and you see the part has been meshed. Now from the main menu bar, go on mesh part. So it asks us OK to mesh the part. We press on yes, and the meshing has been completed. Now the final step is to create and submit a job. To do so, we go on the analysis tab, jobs, double click on job, create this job, submit, continue, leave as it is, everything as it is, press on OK. So now we right click on job 1 and submit it. So if you monitor this area, you will see that right now it's submitted, and then soon it will be running. Now it's running. The job has been completed. Now we right click on it and go to the results option. So now we'll be reviewing the analysis results. So we go to the plot tab in the main menu bar and select on deformed shape. So if I zoom out, you can see the deformation due to the pressure that is applied to the top face. Now we go back to the plots tab, contours, and select on deformed shape. And now over here you can see the one misses stress that is applied to the beam. And here this is the legend which represents the misses stress at different parts of the beam. Now you can save your results, and that's all for the first tutorial.